Thank you. I would like, well, David already did it at the beginning of his talk, but I would like to once again invite everybody to thank the organizers. So Andrew first and foremost, and also Wiegleik and Mark and Julia. Let's see, I don't know where they are. And okay. So great. I want to tell you about KZNs today, and we'll start with some examples that for low n that you probably all know. So let's see, what do we know for low n? If I take n equals 0, well, Z, the discrete topological space, is good. I like it. If I take n equals 1, S1 is a very nice model for KZ1. C star is something that also quite a lot of people like. If I take n equals 2, then most people will say KZ2 is CP infinity. So this is the set of all lines in C infinity. And let's see if we really like this. So the set of all lines, that's great. C infinity, on the other hand, feels a bit artificial. So I want to keep the set of all lines, and I want to throw away C infinity. And so the set of all lines, well, has a few issues. First of all, it's not a set. And second of all, even if it was a set, it's not a KZ2. But if you replace that with the stack of all lines, then there is a way to associate the homotopy type to this stack, and the homotopy type is that of KZ2. So I think of that as a bit more elegant way of giving a KZ2, because it doesn't depend on something that, to me, is a bit of an artificial choice. So there's a relation between this and that. Namely, this is what you obtain by applying the classifying stack to this. If you took your lines to be equipped with a metric, then it would be the classifying stack B of S1. If there's no metric, then it's B of C star. And there's a formal way of going on. You can take, again, B of this, and you get a 2 stack that's like the 2 stack of all U1 gerbs. And then you can do it once more, and you get the 3 stack of all, and so on, and so on. Let me tell you right away that I won't go in that path. I mean, you can do it. It's interesting. But I want to do something else. So let's see. So this is So I would like to think about some other models of KZ2 that I can use, other than this, in order to, by applying B to them, get a model of KZ3. So you need a KZ2 that is a group. And in order to I was being distracted. So suppose I have a big contractible group that contains S1 as a subgroup. Then if I take the quotient group, that's going to be a model for KZ2, and B of that is going to then be a model for KZ3. So I have a candidate for that. And so let's see. So let's consider so this is the you take an infinite dimensional Hilbert space H, you consider its unitary group, and that group has all the desired properties. There's a theorem by Kuiper that says that that group is contractible. It contains a subgroup which is isomorphic to S1, namely the multiples of the unit. If I take the quotient, that's a projective unitary group, and that's a KZ2, and therefore that is a KZ3. I'd like to spend 1 minute making a comment about Kuiper's theorem. So he proves that theorem when U of H is equipped with the norm topology. So there is a notion of norm on operators, and you can use that to make this into a metric space, and then that's the topology that he proves that this is contractible in. And for most applications, that's actually the wrong topology to consider. The correct topology, or the one that I found to be most useful, is the one that makes this into a Polish group. Polish group is a completely metrizable and separable group. With the norm topology, this is not separable. If I view this as a subset of the set of all operators, all bounded operators on a Hilbert space, so these are the ones that happen to be unitary, the set of all bounded operators, denoted B of H, that has a zoo of different topologies. They go by different names. There's like the strong operator topology, the weak operator topology, the strong star topology, the sigma weak, the sigma strong, the compact open topology. These are all different topologies. But when restricted to this group, they all become the same topology. And that somehow can be blamed on the fact that this is a Polish group. Because there's a general abstract theorem that says that if I have two Polish topologies on the same, if I have a homomorphism between Polish groups, which is a bijection on points and which is continuous, then it's actually an isomorphism it's a homeomorphism. Anyways, with that topology, Kuiper's theorem is actually very easy to prove. With the norm topology, it's a difficult theorem. It's a difficult thing. But with the correct topology, it's a super easy theorem to prove. So let me show you a proof of that. So
excuse me, I must be stupid. You're dividing a contractible space by S1?
yes,
So you should get B of S1.
that's right.
But B of S1 is KZ2.
That's correct.
But you're saying, oh, P of Q. Okay. Okay, thank you. You
So
answer it.
I'm pretty sure I didn't, but let me answer. So this is a KZ2. If I apply B to it, I get a KZ3. Yes. This is modding out by S1.
Okay. I misunderstood.
So let me prove for you that this is contractible, because it's super easy. So if I have a unitary, an element of the unitary group of, and now let me pick my Hilbert space conveniently for the purpose of proving that. I'm going to pick it to be L2 of the interval 0, 1. Then I'm going to construct for you a canonical path between 1 and u. And the collection of all these canonical paths is going to be an alpha is going to be a contraction of this space. So let me call that u sub t. And what is that canonical path? So u sub t acts on this Hilbert space, which I'm going to decompose as L2 of 0t. Okay. So let me say again in words what I'm doing. So I'm taking the interval 0, 1, and I'm splitting it into two pieces. I'm sort of, here it is, and I'm splitting it at point t. So I write my Hilbert space as the direct sum of functions here and functions there. And on this piece, I act by u, or rather I act by, well, first take the isomorphism between that and that, apply u, and then go back by the isomorphism. And here, I do nothing. So you take your unitary thing, and you let it be defined on a smaller and smaller and smaller piece, and eventually it goes away, and that's continuous. So that's great. So once again, let's look at that construction and see if we like it. First of all, this group here depends on a choice again. It depends on a choice of a Hilbert space. And so I'll address that later. But for the moment, let's say that we can live with that. Then the next step was to consider this, the quotient group. And here you might very well argue that the only reason I performed that operation was in order to get what I wanted. It's not like something that I would naturally do. It's something that I had something in mind, and then I did it in order to achieve my goal. And that's not what I want. I want something which really is like you do something else, and then you find this. So, I mean, it's like in like when you had your first group theory class. Like quotient groups are always kind of difficult to understand because they're not groups that act on things. Like a group is made to act on something, and a quotient group, I mean, its elements don't act on H or. So in order to convince you that this is a natural thing to look at, I want to give you something that is very natural on which this acts. Even more, I want to show you something such that this is the group of automorphisms of that object. So this B is not that B. This is the algebra of all operators, of all continuous operators, all bounded operators on my Hilbert space. And I claim, and I'm going to show you, I'm going to prove this little fact to you in a minute, that this is exactly the automorphism group of that algebra. So first of all, let's see that this group indeed acts here. So how does one show that a group acts when the group is a quotient group? Well, you first construct an action of the big group, U of H, and then show that the subgroup S1 acts trivially. So what is the action of how, given a unitary, can I construct an automorphism of this algebra? Conjugation. And indeed, if my element is in S1, and S1 consists of central operators, then conjugating by something central does nothing. And therefore, this action descends to an action of that. So that's not the difficult part. Now I want to actually prove to you that this action exhibits PUH as the full automorphism group of B of H. Let's see. Here. Proof of this. I'll first show that every automorphism is inner. Namely, that the map from here to automorphisms is surjective. And I'm going to use the following that there's a Morita equivalence between those two algebras, between the algebra of all bounded operators and the algebra of complex numbers. And that's certainly not an algebraic kind of Morita equivalence. So algebraically, the complex numbers is going to be Morita equivalent to the algebra of n by n matrices for any finite n, but not for n taking the value infinity as I want to do it here. But if you go to some analytic context, then you can push this Morita equivalence to a setup that does include this. So for the moment, let me take that as something that we accept, and let me use it to show this. Suppose I start with an automorphism. Which I'll call alpha. Then I can use that automorphism to construct. So let's see. This Morita equivalence is implemented by a bimodule. And the bimodule is the Hilbert space H itself, with a right action of the complex numbers and the left action of B of H. If I have an automorphism of B of H, I can twist that left action by the automorphism. That's a new bimodule. So given alpha, I'm trying to show something about alpha. I'm trying to show that alpha is inner. Given alpha, I'm going to construct that object. Using the Morita equivalence between B of H and C, I can go back and forth between B of H C bimodules and C C bimodules. But C C bimodules are very easy things to understand. So more specifically, this is an invertible bimodule between B of H and C, and invertible C C bimodules are very easy to understand. They're just one-dimensional vector spaces. So if I transport this using that Morita equivalence to a CC bimodule, I get something which is an invertible CC bimodule, and all invertible CC bimodules are just isomorphic to each other, and therefore all invertible B of H C bimodules are isomorphic to each other. So what I learned using this is that there exists an isomorphism of bimodules between this one and that one, because they're both invertible bimodules. Let's call that isomorphism U. And then you just write down what it means that U intertwines the actions of B of H given by, well, here the usual action, no twisting, and here the twisted action. And what you see is that that equation is exactly the equation that says alpha equals add U. Great. So that's one half of the proof. The other half of the proof is to show that this homomorphism from here to here, well, we've shown that it's surjective. Now we need to show that it's injective.
What are the distinction between unitaries and all invertibles?
Well, let me not ignore the distinction and then impose the condition that this isomorphism be unitary. But, I mean, this is going to hold in any case. If I take this isomorphism to be 2 times a unitary, then I'll have, again, this is going to hold. So,
I mean, the full automorphism proof of the bounded operators is the projective general linear proof, not the projective unitary.
So then let me say that I want to look at the automorphisms that respect the star algebra structure. And then I'll have this to be a unitary, and then this holds. So the next step is to show that the kernel of this map is just S1, which is to say that the map from PUH to automorphisms is injective. For that, I'm going to rewrite this kernel as, so we're trying to show that kernel is the center. Things that, this is the conjugation action. This is add. And an element U such that add U is trivial, that's an element that's central. There's the center of this group. And then you can rewrite this as, well, let's try to understand the center of this algebra of bounded operators. That's, if we understand that, then we can cut out the unitaries in there. That is the same thing as the endomorphisms of B of H as a bimodule over itself. And that's the identity bimodule for B of H. And again, using that Morita equivalence, you can go back and forth and replace B of H by C everywhere. And so what you see is that that's the same thing as the endomorphisms of the identity bimodule of C. Well, that's easy to compute. That's just one-dimensional. That's just C. Or if you want to insist on unitarity, that's just going to be S1. And so we get this thing here. So now that we have phrased things in that way, there's also, we've also learned of a new name for this here. So this before was just the moduli stack of PUH principal bundles, not a particularly attractive thing to look at. But now that PUH is identified with the set of automorphisms of B of H, this becomes the moduli stack of this becomes the moduli stack of algebras that are isomorphic to B of H. And phrased in that way, that's again not super attractive because it looks like I've just like made a construction and I like looked at everything that is isomorphic to my given construction. But this can actually be characterized in a sort of axiomatic setup. There's like a set of just things you can write down, and then so let's see. These are called type 1 factors. So there's an abstract notion of a type 1 factor. These are certain special class of von Neumann algebras. And then there's a theorem that says that every type 1 factor is isomorphic to B of H. If until now you didn't know what a type 1 factor is, well, that's a definition. But there's a better definition that makes it look like this is a natural notion. OK. Something else which is kind of pleasant with this description is that I've eliminated the choice of H. Before, well, we had to fix an H in order to define U of H. And I said that that was a little bit unpleasant because it's a choice. If I just say the moduli stack of type 1 factors, that does not involve that choice. It's just like an object which is like out there.
It's like binomials with certain properties.
Yeah, these are von Neumann algebras that are factors. So a factor, for a von Neumann algebra to be a factor, it means that its center is one-dimensional. So this condition here, the center is one-dimensional. Let me. And that the set of projections admits minimal elements. So there's like minimal projections, and that's and then I guess also infinite dimensional in order to exclude the finite dimensional algebras. So let me give you some reasons why I like that description. One of them is that it's a flexible thing. You can modify some of the ingredients that come in here to get some other interesting homotopy types. For example, and here's what I have in mind, you can replace the complex numbers by the reals. If you replace the complex numbers by the reals, well, OK, nothing much happens, except at this very last stage, when you classify type 1 factors, you see that there's two isomorphism classes. Like there's matrices over R and matrices over the quaternions. And essentially, that's everything. And so you get an interesting homotopy type. Well, not so terribly interesting, but it has pi naught, which is Z mod 2, and then also pi 2, which is also Z mod 2. You can also do the same thing in a setup which is in a Z2 graded setup. Again, both for complex and for real, and you get some homotopy types that show up that are interesting. But really, the reason why I like this model is because of its direct connections to twisted K theory, and David Gepner gave a beautiful introduction to that. So let me continue on what he said. So suppose I have a topological space X and a map to the stack of type 1 factors. Well, what does it mean to have a map to this set of all algebras that look like B of H? It means that you have a bundle over X whose fibers are things like B of H. So you get a bundle of algebras over X. And now if you take the way you define K-theory, but instead of using vector bundles over X, you use bundles of modules over that bundle of algebras, then what you get is twisted K-theory. So there's a very nice direct connection to twist of K-theory. Great. So this was the first half of my talk. Now I want to tell you about what comes next. The motivation for looking for nice models of KZ4 is, again, David Gepner spent some time at the end of his talk talking about that, is that KZ4 controls certain twists of TMF. And let me remind you very quickly how this goes. So if I have a spectrum E, then E cohomology for any spectrum E admits twistings by vector bundles. More generally, it admits twistings by spherical fibrations. And that's how it goes. So if I have a spherical fibration over some space X, then I can take it and fiber-wise smash with E. And then what I get is a bundle of spectra. And sections of that bundle of spectra that's twisted E cohomology. So that's a general setup. Now let's take E to be TMF. Then, so what I described to you is a map from vector bundles, let's say BO, to BGL1 of any spectrum, let's say TMF. So that's the thing that classifies as twists of my cohomology theory. And by a theorem of Ando-Hopkins-Resk, if you precompose that with a map from B string to BO, then that's null homotopic. Equivalently, if I consider the cofiber, which is BO modulo B string, there is an extension of that map across that cofiber. And what does that cofiber look like? That cofiber is a spectrum with a small number of non-zero homotopy groups. So let's see, if I write it like that, really I should have written Z cross BO and Z cross B string everywhere. No, sorry. Z cross BO, but not Z cross B string. I'm all confused. So this is pi naught, pi 1, pi 3, pi 2, pi, did I? 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Great. This is degree 4, and so there is a map from KZ4 here, which, if you compose it that way, produces a a supply of twists of TMF by KZ4. So that was the motivation. Now let me tell you the construction. So that story up here had essentially one big analytical input, which is the notion of a Hilbert space. And what I'm going to have here is also going to have essentially one big input from analysis, and that is going to be a particular kind of von Neumann algebra, the so-called hyperfinite type 3 1 von Neumann algebra. So let R be the hyperfinite type 3, 1 factor. So factors are classified into three types: type 1, type 2, type 3. And the type 1s you saw there. Type 2, I'm not going to say anything about them. Type 3, that's a type 3 one. Type 3s are then subdivided into further subclasses, 3 sub, and here you can put any index you want between 0 and 1, and that's a particular one. Just like the infinite dimensional Hilbert space, this thing is unique up to isomorphism. There's only one of them. I mean, it has a huge automorphism group, but it's unique up to isomorphism. And just like for Hilbert spaces, there's many, many constructions of this thing, and the constructions look very different from each other. But because presumably you've never seen this, I'll just give you one construction, and then you know what I'm talking about. So what the thing is not going to play a big role, but here. So let's consider the following action. So the units in Q, semi-direct product with L infinity R, that's an algebra. And this is a Hilbert space of functions on this product, here with a counting measure and here with a Lebesgue measure. And let me tell you how an element here, so let me call it Q comma F, so that's an element in here, acts on a function. Let me call my function Xi. And let me tell you how that evaluates on an element in here, which I call X comma Y. And that's just a formula. That's F of Y, Xi of QX, QY. OK, that's an algebra acting on this particular Hilbert space. And now if you take the closure of that algebra in, for example, the topology of pointwise convergence, then you get this guy. So the closure is isomorphic to R. And really, what I needed as an input was just a measure space and a group acting ergodically in a way that does not preserve any measure. And then you can make this same construction. OK, great. Let me now tell you what we will need to know about R. This we won't need to know. But what we will need to know is that it's a factor, which is to say the center is one-dimensional. Then there's an analog of Kuiper's theorem, which says that the unitary group of R, which is to say the intersection of the unitary group of that Hilbert space with the algebra, is contractible. And then there's a third item, which is less trivial, which is that the automorphism group of R is also contractible. That fact is, I believe, due to Anthony Wasserman. Well, he didn't write it up, but I think he proved it. And I think that at this point, I also know how to prove that. Anyways. With that information, we can now go on and make the following constructions. So the center of the unitary group, that's just S1. And if I mod out by S1, I get a group which is a model for BS1, just like before. That's contractible, and that's what I mod out by. If I look at automorphisms of R, I can consider the subgroup of inner automorphisms. And the quotient, which are the outer automorphisms. And the thing to note is that inner automorphisms are exactly the same thing as unitaries modulo those unitaries that act trivially, right? By definition. You take unitaries, you let them act. These are the inner automorphisms, and certain unitaries will act trivially, namely those from the center. Let's see. That was a KZ1. This was a KZ2. Therefore, that's a KZ2. That's contractible. That's what I have here. Therefore, that's a KZ3. And if I take B of it, that's then my KZ4. There's a grain of salt in this whole story, which is, whereas these groups are very nice topological groups, they're all Polish groups. That inclusion here is dense. And therefore, this is not a topological group. Or if you view it as a topological group, then it's not a KZ4. But the best answer is to say that it's not a topological group. What it is, well, you should take the sheaves represented by these things, sheaves on the category of all spaces, and take this to be the quotient sheaf. And a sheaf has an associated homotopy type, because you can form the singular complex of that, and that homotopy type is going to be that of a KZ4. So that's a sheaf on topological spaces. Yeah, it's a group object in the category of sheaves. So my next goal is to convince you that that's a natural construction. Because really, maybe you've already sort of wanted to stop at this point. You're like, oh, this is a dense inclusion. Maybe it's a bad idea to take this quotient. And then furthermore, taking B of that, maybe that's like overkill. So I want to convince you that this thing comes naturally, namely that there's a natural object that one could consider of which this is the automorphism groups. But first I want to say a little note, which is that one way of understanding autoautomorphisms of R is as isomorphism classes of RR bimodules, invertible RR bimodules. If I have an automorphism of R, I can use that automorphism to take an RR bimodule and twist it on one side, and then this equivalence relation ends up killing the inner automorphisms. But that in itself is not really justification why that's an interesting group, because again, there's like this ugly quotienting operation. So here's the claim, is that that's the automorphisms of something, and let me tell you what comes in here. What comes in here is BIM-R, the tensor category of bimodules. And automorphisms here, I mean automorphisms of tensor categories. So let me first try to convince you that this group here acts on BIM-R. So what do I need to show to construct an action of that group on BIM-R? Well, I need to construct an action of automorphisms on BIM-R and trivialize that action on the subgroup of inner automorphisms. And well, clearly I'm not topologizing because I don't want to get a topological group. So you need to do something else. You need to equip it to the structure of a sheaf on top. So that's a good question. I actually confess that I haven't thought about that point at this thing. So what I know how to show, and again, it's not a complete proof. It's a sort of sketch of proof modulo some assumptions, is that this is really at the point set level, it's an isomorphism. And then let's say it's work in progress. But it's a very good question. I mean, it's important to. So, the automorphisms of R clearly act on BIM-R. I mean, BIM-R is determined in terms of R. If I have something which is constructed in terms of R, an automorphism of R, it induces an automorphism of this thing. So that's easy. And then I need to trivialize it here. So the action of so let me write down the action. So suppose I have an element in here, and I want it to act on a bimodule M. That is going to be the same bimodule, but where the actions are twisted on both sides by alpha. Right? I mean, I want to twist on both sides. Otherwise, if I twist it just on one side, it wouldn't even send the unit object to the unit object. Right? If I take the unit bimodule twisted on one side, it's not the unit bimodule anymore. If I twist it on both sides, I want automorphisms as tensor categories. So I twist on both sides. So now I want a trivialization of the action of the inner automorphisms. Great. So an action of this was an action of that and a trivialization of that, of its restriction to this. Now, a trivialization of the action, and now I go through here, a trivialization of the action of this group is going to consist of a trivialization of the induced action here, and that trivialization, I need to make sure that it does nothing here. The trivialization of the action of u of r needs to be trivial when restricted to that. And then it is indeed a trivialization of the action of this. Otherwise, it's something else. So a trivialization of the action of this is a trivialization of its restriction to u of r that does nothing for elements of this guy here, S1. Good, so we're going to look at that formula up there, and instead of alpha, we're going to put add u. So we take an element u in here, and I take alpha to be add u, and see what we get. So I take m and I twist it by add u on both sides. So I take u in here. And I want a trivialization of that, meaning I want an isomorphism between my bimodule without twisting the action and the bimodule with twisting the action. And multiplying by u on the left and by u inverse on the right, as a map from m to m, intertwines the untwisted action with the twisted action. Moreover, if I take u to be in S1, well, look at what you have. I have something, and it's inverse. And therefore, it does nothing. So that's good. That's providing an action of that group on BIM R. So now I want to convince you that that action has a chance of inducing an isomorphism. And I'll only do one part of the proof, so piece of proof. And I'm only going to prove the part which is analogous to what I have up there, that the homomorphism from out R to automorphisms here is surjective. I'm going to prove surjectivity. So here there's a map, claim a proof of surjectivity. And I'm going to use something which is actually a rather strong assumption, that BIM R is Morita equivalent in an appropriate sense to BIM C. And the Morita equivalence bimodule is given by R mod as a BIM R BIM C bimodule. So if I have a module for R, I can tensor it to the bimodule, I get another module. And here, well, that's a very boring category, BIM-C, that's just CC bimodules, that's just vector spaces. So now I'm going to copy this argument. Formally, it's going to work. Let's see. I do it here. So we start with alpha in the automorphisms of BIM R. And I'm going to use alpha to twist that Morita equivalence bimodule. So we have R mod, which is now a BIM R twisted by alpha BIM C bimodule. And using the Morita equivalence, we can replace BIM R by BIM C. And now I claim that any two BIM C invertible bimodules are isomorphic to each other. So a BIM C invertible bimodule, that's a mouthful, but that's really not very frightening. BIM C is just vector spaces, and having an action of vector spaces is just like nothing. So I'm just saying that invertible categories are, and this is a setup where like every category is like over vector spaces. So really, I'm saying that there's only vector spaces which is invertible as a vect module. And transporting that statement via the Morita equivalence, we get that any two invertible BIM R, BIM C bimodules are the same. For example, the untwisted one and the twisted one. So the difference here is that there's like an alpha, and here we have an equivalence. But a map from R mod to R mod that's given by a bimodule. Every map is given by a bimodule. Let's call that bimodule M. And then you unpack what it means that M is equivariant with respect to the action that intertwines it untwisted with the twisted action of BIM R. And what you see is that alpha is add M. And if you use the fact that bimodules is really the same thing as automorphisms, then you can sort of actually find an element in here such that alpha is given. So this proves surjectivity. So now we can go back and think about what this beast is. Well, that is going to be the moduli stack of things that look like BIM R. So now I don't have an abstract characterization of things that look like BIM R, but okay, except things that look like BIM R. And my hope is that this description will shed some light on the project of finding geometric co-cycles for a TMF, because whatever a geometric co-cycle for a TMF is something that should be twistable by one of those. If I have a space and a bundle of things that look like BIM R, then there should be a notion of bundle of something with action of this bundle of tensor categories that somehow connects to co-cycles for a TMF. Well, on that note, thank you very much.